Thank you, everybody, for joining us today. The topic today is a continuation of the signal integrity. We already did part one, which was kind of like an overview, and part two, we started getting a little bit more specialized. And today, we're going to be doing part three, and Jorge is going to be giving us a kind of a detailed explanation of the continuation of how you can work on your design and be taking into consideration your signal integrity. So I'll go ahead and stop sharing my screen. That way, Jorge could share your screen. Okay, Jorge?
Okay.
Excellent. Please leave your questions for the end, if you don't mind. That way, we don't have to address them throughout. We don't have to interrupt Jorge. So we'll have like I would have to say like a 15-minute Q&A session at the end, and we'll address all your questions. Go ahead and use the chat, or you could use the Q&A as well. Well, thank you very much. Appreciate it. Okay, Jorge.
Okay. Give me 1 second. Just going to open this up.
Well, I'm not seeing your screen yet. I'm not sure if you're sharing yet.
No, not yet. Just want to make sure I open up this other one first. There we go. Okay. Can everyone see? Sharing screen now.
It's coming up.
Okay.
Perfectly. Yeah, I see it just fine, Jorge.
Okay, cool. So, hello everyone. My name is George Garcia. As you guys know, we've already gone through parts 1 and 2. And in this one, we're going to talk a little bit about transmission lines. Now, fundamentally, the only thing you need to have a transmission line is 2 conductors. One for the signal to go through and a return path. Okay, so that's fundamentally what you need. Now, let's talk about a few things. If you notice, I've shown 3 models here, starting from the easiest or the simplest to the most complex. Now, as you know, most of the time when you're working with your circuits, you probably don't even think of the first model. You know, everything is treated as an ideal wire, an ideal connection, no losses in the wires. You know, everything is transparent to your signals. And for most of the low frequency stuff that maybe some of us are used to working with, that's fine. You know, we're not dealing with anything high speed, any type of high frequency, or anything where the lengths are very big. So if you're dealing with high speed, high power, or the traces are long, maybe you're dealing with large interconnected systems, then you start to worry about these things. Okay. Now, the idea with each of these models is to go into progressively more detail depending on the need. So the zeroth order model is the most basic. It helps establish engineering intuition. And what you see is probably some of you are noticing that I've placed multiple capacitors when obviously you could replace all of that with an equivalent capacitor. But the idea here is that in the zeroth order model, you're basically dealing with capacitance per length. So you imagine you're walking, you're the signal walking down this transmission line, okay? And at every step, you're running into a capacitor and you're charging it and then moving on. Okay, so this is what a real signal does. So if you have a, let's say you have a pair, okay, and you connect a battery to it and the other end's open, okay, as soon as you put a meter to it, it's going to read as an open circuit. But if you were able to freeze time and you were able to go right after the instant in which you've hooked up the battery to the end of the wire, you'd actually see that there's this wave flowing. So at each step of the way, you have this wave of an electromagnetic field that's moving along the length of the transmission line, and along the way, charging up these capacitors. Okay, and you can use these capacitors to establish a characteristic impedance for the line. Now, obviously, in most of the real world cases, you wouldn't be able to measure that. It would happen so quickly and it would become open because at the other end of the transmission line, right now we have it open, that it would just read open as soon as you could get a probe to it. But imagine that you had a transmission line that went from the Earth to the Moon, about 240,000 miles, total round trip, okay? Well, knowing that, if we thought about that for a second, what would be happening at the ends of this wire? What would we be seeing at the end of this transmission line that's so extraordinarily long? Okay, well, if you were to put a battery to it, then the voltage signal would propagate at the speed of light in that medium. Okay, as we know, the speed of light is roughly around 138,000 miles per hour, roughly. I might be off there a little bit, but round trip, that would take about 4 seconds to do. And in those 4 seconds, if you were to hold the battery and you had a meter there, you would actually be able to measure current flowing through that until the whole round trip has completed and all these capacitors in that transmission line have filled up, and then you would read open, assuming that you didn't have anything connected on the other end. So what you're looking at here is the behavior on nanosecond timescale. You know, in hundreds, in kilohertz, hundreds of hertz, kilohertz range, you don't see any of this. But as you start going into higher frequencies, these behaviors become apparent because the higher the frequency, the shorter the length it takes for these behaviors to be observed. So if you're in the gigahertz, you don't need wires going from here to the moon. You need wires going from here to 3 inches away, here to half a ruler away, and you can start to observe these effects. Okay? So that's the idea. That's the intuition we want to start building. Now, obviously, going to the next level of accuracy, if you do have current returning, then there is a loop inductance involved. And that's what the next model shows. Okay, these inductors represent that loop inductance, which does have an effect on how the transmission line behaves. But again, now you're getting into more detail. The last model is very important because this one is the most general. In the case of the lossy model, what we end up having is we're able to see that the attenuation of a signal isn't fixed. Okay, so if it were just dependent on the length of the transmission line, it would be very easy. But because we have these capacitors and inductors with these resistances interacting, the loss is frequency dependent, and that's what makes this harder to work with. So if you're dealing with very high frequency signals and you want to make sure you have good signal quality at both ends, then you have to take that into account. So it all depends on the type of situation you're dealing with. Now, I wanted to come up with a good simulation to kind of show how we could use this. And the example I came up with is actually one that is in a low frequency regime, but can be affected by length. So it's something that can more tangibly be felt when you're working with it. So let me go ahead and open up that example. So I'm going to go save this, file open recent, and this. Any musicians in the audience? Anybody go ahead and raise your hand and ping us if there's any musicians in the audience.
Yeah, Jorge. Yes, for everybody to know, Jorge is a musician himself.
Okay, so let me go ahead. Oh, we got a few. We got a few.
Yeah,
We got
Leo's a musician.
All right, we got a few coming in. Nice. So let me go ahead and fix a couple little things here, make a few connections here. Okay. So what I'm modeling here, again, we have these multiple capacitors, which again, I could really replace with one. And if everybody is okay with it, and we understand that this capacitor is going to represent the total capacitance in the wire, if we can clear that up and everybody's okay with that, then I am going to replace these with just a single capacitor because it'll just be clearer. It'll be easier, I think. Okay, everybody agrees? Everybody cool with me doing that? Yeah, we would just be doing some
Yes.
multiplication. That's all we
Yeah,
would be doing.
it's adding the value of each one. Okay.
Okay, so we're going to do that. So let me put this over here. Okay. There we are. Okay, and let's put in some nice explanatory notes. That way everybody knows what's going on over here. Okay, and actually, I do have to put something over here. Almost deleted my op amp. Okay. We got that, got this going on. So what we're going to model here, and this is a can be a very controversial topic, but basic engineering principles can help us come to a conclusion about how we should handle the situation that we're going to be discussing. Okay, I'm going to put that there. And again, we have a single-ended signal with a common return path. Okay, I'm going to go ahead and write text so we can all be on the same page. Okay, input. Okay, let me put this info right here. Okay, C total is equal to C per length times the length. Okay, that's what we're dealing there. Okay, let me put all this over just a hair. And what I'm going to put here is going to be a really big cap. Okay, very handy feature if no one's seen that. You can place components within a net and Eagle will make space for them. It will automatically adjust. Oh, you're muted, Ed. You're muted.
Yeah, it will actually split it, so each N is a different signal name.
Okay, gonna put this here just so that the op amp can swing where it needs to. Okay. And I'm just gonna make this some ridiculous value. That way the signal just goes through unaltered, but we get the DC bias we need for the op amp to be able to track it. So value, just put like 1 farad. Something ridiculous. Okay, so now, basically, let me draw this actually. This will be, need to draw this in also. Short dash. Okay. Okay, excellent. So basically, from the dash line over to the left, that's basically the inside of a guitar or a bass or any type of stringed instrument that uses magnetic pickups. Okay, I've purposely excluded a tone control just before anybody gives me grief about that there's no tone control. There normally would be, but I've excluded it in this case just for simplicity. Okay, so I'll put */bass over here. Okay. Nice. All right, excellent. So what are we going to model here? Okay, typical cable, run-of-the-mill, not super great, not super bad either, is about 40 picofarads per foot. Okay. Let me actually write that all out so we see it. Farads per foot. Okay. Let me write that bigger. Now, why is this important? Well, this becomes important because if you have really long cable, then you're going to have a significant capacitance loading down your guitar circuitry. Okay. Now, up here, we've modeled a passive instrument. Okay. So this type of instrument, it doesn't have any type of, doesn't use a battery, doesn't have any type of active amplification, okay? And it's also not buffered, okay? So its impedance is going to be mostly dictated by whatever the volume pot is. And that's what these two resistances here are representing, okay? This is basically a 250 kilo ohm volume pot, okay? So the lower the resistance feeding this line, the less deterioration we have arriving at the amplifier input. And I've used a simple resistor, a high value resistor, to represent the input of an amplifier. Typically these are high input impedance, specifically for the reason of being able to receive a clean voltage signal. But we have this capacitor, which we're going to use to model the length of our cable, okay? So on a typical instrument, and let's say we have 40 picofarads per foot. Let's say we have a 20-foot cable, okay? So if we have a 20-foot cable, we have 800 picofarads, right? Everybody agrees with me on that one? So I'm going to say we're going to use a 20-foot cable. Cable, 20 feet times 40 puff per foot is going to equal 800 picofarads. Okay, everybody with me there? Check my math. If I screwed it up, it's okay. Okay, so now we're going to go into value and go over here. And we're going to put 800 pico. Okay, we're going to do the same thing here. 800 pico. Okay. Now, what do we want to get? We want to get our value. We want to measure our voltage at the input of the amplifier in both cases. Okay, let me give these names so that they make sense. This will be V passive. Yeah, it's okay. I don't want the label. And this one will be V active. Okay, what makes it active is that we have this buffer, this op-amp buffer right there. Now let me take off the label. Don't want that. Okay. And in this case, we have the same input signal for both, so I only have to measure it once. That way we avoid wasting that. So let me put in a name for that one. Just VN. And we'll again put a voltage probe here. Now, if anybody's wondering where I got these values from, this is typical inductance for a pickup, and this is typical DC resistance, 14K and 6 Henrys. You'll find, depending on the pickup, it can vary pretty wildly. So usually you'll see like between 3 to 7 is typical for the 3 to 7 Henrys for the inductor. And then the DC resistance can be like from 8 to like 20 something, depending on the situation. Okay, but the main values here aren't that important. Now what we have here, okay, what I'm feeding is a square wave that goes from -60 to +60 millivolts, and it's going at about 100 hertz. Okay, that's the idea. 100 hertz. So I know real instruments do not output square waves. We know that. But I chose a square wave because it has a very sharp edge, and we're going to see that that sharp edge is going to start to round off because of this cable capacitance. Okay? And we'll observe that if we have active circuitry, a buffer, then that effect is neglected. Okay? So let's go ahead and form our simulation. Now, a couple of things we want to talk about here with the simulation. We're going to do a transient. You generally want to have your transient simulation set up in such a way that you're getting the steady state, number one. And number two, you're trying to get 5 to 6 cycles in the window, especially if you have oscillatory behavior like we do here, where we have a square wave coming in. You want to make sure that you don't have it running for too long a time, because that can make it difficult for it to converge. Okay, so keep that in mind. So start time, I'm going to give it a few milliseconds, or actually let's give it 1 second. And then we're going to go the stop time. We're going to say if we want 5 cycles at 100 hertz, each one is 10 milliseconds is the width. So it'll be 1 point, let's do 1.05, 1.06. Okay, 1.06 seconds. Okay. And now we can go ahead and try to simulate it. Let's see what we get. Alrighty, so let's take a look here. Have lots of currents, lots of other things going on. So the signals here. Apply changes, okay. Looks like I have something, so the active goes clean. Have here, it's a passive. And then right here we have the VN, but the VN shouldn't be going like that, unless I did something wrong in the setup of the waveform. So we have 10 milliseconds here. But this is going for too short, so I must have put something wrong in the timing of it. Because it should be low for at least 5 milliseconds. So let's go ahead and fix that. Okay. Analog source setup. Pulse, AC value, DC value. 0, that part's okay. Millivolts, let's make sure. Delay rise time. Width is 10 milliseconds. Ah, I did it backwards. This should be 5, this should be 10. There we go. Same thing here. There we go. Let's try this now. Ah, better. Okay, good. Good, 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 good. Let's go to our signals now. Okay, we don't care too much for the VN, although you can see it's rounding off a little bit, but nothing noticeable. But the V active isn't working. And I think I may know why. Okay, let's do this. Let's go over here. This is all a normal part of troubleshooting these types of circuits. Let me go ahead and change this, because in real life you would have something different here. Let me just put in a 4.5 volt offset here. Okay, so we would have 4.5, DC value would be 4.5. Okay, set the value there. And let me get these out. Oh, I still have it on the short dash. Yes, okay. So we wanna, let me make sure this looks like the way it should. Yes. Okay. This should do it. Okay, good. Now I think we got it. Type it into this out. Okay, apply. Let me take off VN. We all know it's an in-phase square wave. Apply changes. Okay. So we're going to see active one has a bit more, still maintains a bit more volume, obviously. And then we see here, if we actually, well, come on, zoom. We'll see that the active one is preserving the high end just a little bit better than the passive one. Okay. You can see that. Active one green is preserving the sharpness of this angle a bit more than the passive. Now, I've done something to make the passive look good here. And what you're going to notice is that what I've done is I've set up its potentiometer to have a relatively low volume. Okay, so right now on this 250K, what's visible to the rest of the circuit is really about 50K. Okay, because you take all of these impedances at the various frequencies, and really what ends up dominating is this resistance here. But what happens if we now have max volume, which is what many of us may do? Okay, in that situation, things may change a little. So let's go ahead and explore that. So I'm going to go values. I'm going to put this as 1 ohm because you don't want to have a dead short. I'll make this 250K. Make this one 250K. And I'll make this 1 again. Okay. So now let's go ahead and simulate it and let's see what happens. Oof. Okay, so now we have high volume going on. Again, because I use squares, probably some heavy duty transient behavior. Let's go ahead and turn off these currents. And I'm actually going to turn off VN too because we don't need it. Okay. Now let's zoom in. Okay, now what we've gotten is our signal is actually resonating. It's turned out that the specific values that are created are giving a bit of overshoot. And again, this is just because we have a square wave. Okay, but what you can observe is that the active signal still preserves its dynamic range. Okay, so what's the point of this? Okay, that the longer your cables get or the more capacitance they have, then the more you're going to see your high end roll off. Or I mean, in real life, you don't get this type of oscillatory behavior because again, you would have a tone control and you would have those things coming into play. But you would see that the active circuit would preserve the quality of your signal much more than a passive circuit because you have this high impedance interacting with this higher capacitance due to the length of the cable. And the more cable you have, the more they're interacting. Okay, so if you had a 40-foot cable, you had a big rig, then what would happen is we would double this to 1600. Or actually, let's do a different modification here actually, because this is also real world. So let me go back here. Let's change the value back to 800. Whoops, 800. Okay. Now, let's say that instead of an amplifier, you're going into maybe an effects unit. Okay. Some of those can actually have very low impedances here. So let's say this is 500K instead of 1 meg. Okay. Over here, 500K. simulate it. Okay, we go over here again, signals, take off all these currents. I left the V in. Okay, again, you start seeing this oscillatory behavior. But you see that your original signal in the active sense is preserved. So what's the key takeaway here? What are we trying to arrive at? Okay, and that's why I called this file tone suck. What can happen in many situations is that if everything, let's say you have lots of effects, you have lots of things before you get to your amplifier, if everything is true bypass, you're basically just adding cable of different qualities, of different capacitances. So this value is getting higher and higher and higher, and it's going to start to interact with your instrument's internal electronics. And typically what will happen is that you'll get high-end roll-off. You'll lose clarity. And that's colloquially known as tone suck. The solution to avoiding that is to having buffers within your chain. Okay, so either you have an active electronics instrument, or you have a buffer at the beginning of the chain, or if you have super long chains with lots of different effects and you have multiple effects that have buffers in them, and all of that, what it's going to help you do is it's going to help you preserve the clarity of your tone. And we can arrive at that thanks to this first order model. Okay? And that's really the power of this model. Now, what I'm going to do is I'm going to go ahead and just as a final experiment, this is something that you can do on your own. You know, you can experiment with values, you know, make different adjustments. I'm going to go ahead and add in a tone control. And I'm just going to put this here. I'll change the values now. Let's go ahead and make a little group. Control C, Control V. Okay. Control C, Control V. Okay. Let's go ahead and copy this right here. Make the connections. Now for these, we typically have 0.47 microfarads. So I'll change both capacitors to be that, 0.047 micro. And I'll have it just at like 100K or 125, the middle of a typical control. Over here, whoops, 5K, hit enter. Let me reposition these to the bottom right, that way. Oh, want a name and value. Here we go. There we are. Just so it's a bit more visible. Okay, and now let's go ahead and simulate it. And maybe by putting this in, I've probably helped clamp down that oscillatory behavior, and it may be clear the interaction here. Simulate. There we are. Help clear that down. Let's take off the VN. Okay, and again, we can see the benefit of the buffer, just keeping everything cleaner. And just no delay. and all of your high frequency content is better preserved with less distortion. So, moral of this lesson, you can use even a simple model like this one to analyze a very typical situation for a musician, or anything involving long length. So if you have large systems, even a simple model like this one gets you an idea of how the wiring may affect your system. So that's kind of what I wanted to show. I wanted to show a simple example applying one of the models, and I thought this was actually very practical and kind of more hands-on, which is why I chose it. And the conclusion is that a good buffer is better for a good buffer is better for your tone than true bypass, because over time true bypass is going to load down your circuitry unless your instrument already has a buffer built in and it's an active instrument. Okay, so that's the key thing we wanted to arrive at today. Any questions, anyone?
No, not yet, Jorge. No, I don't have any questions. Are we at that stage already?
Yep, we're at that stage.
Okay, very well. Well, thank you very much. It actually is pretty informative. So, oh wait. Um, okay, so I don't have anything on the Q&A, as well as I'm looking at our friends on YouTube. I don't see anything yet. So we don't have any questions. Greatly appreciate it. That was yeah, especially using the simulation to be able to prove your point is always very collective. So does most guitar amps are vacuum tubes?
Guitar, yes. Bass, no. Most guitarists would rather eat glass than play through a solid state amp. So yeah, for guitar amps, most are vacuum tube based. They distort in a very characteristic way, emphasizing even harmonics. So that's the sound most people are used to when they hear a distorted guitar. For bass, not so much. Bass is not required. The tube distortion is not a characteristic thing.
Okay. So thank you very much, Jorge. Appreciate it. John, always a pleasure. Thank you for joining us as well. Richard, thanks for being here. All of you, appreciated your attendance. And I'll put our email address one more time on the chat for those that were not here earlier. That way, everybody has, if you have any other questions, you can contact Jorge on our support channel. So I'll put support.eagle@autodesk.com. Also, you could post any questions in this regards on our forum, our very active forum, which Jorge actually monitors very closely. I don't see anything else yet. Well, everybody, have a great day. Thank you for being here. Jorge, thank you very much. Always very informative. Great presentation. Everybody, have a great one. Bye now.
Bye.